Hello everyone, today we are going to be learning about section 12.2 and polar coordinates. So it is entirely possible that you guys have learned about polar coordinates, perhaps in a physics course or somewhere else. But in section 12.2 we're going to be learning all about how to graph polar functions, what polar coordinates are, how to convert between Cartesian coordinates, basically everything you can do with polar coordinates that does not involve calculus. Section 12.3 will be devoted to learning about the calculus behind polar coordinates, and that will be all we do in Math 1080. So we're almost there. So let's just go ahead and jump into it. First of all, let's consider the fact that in most of your time in mathematics, you have been exposed to what we call Cartesian coordinates or rectangular coordinates. So if I told you to plot a point 2, 4, you would move an x distance of 2 and a y distance of 4 and then draw a dot. And that's how most of our Cartesian functions are as well. They're, y equals f of x. Today we're going to introduce a brand new system called polar coordinates. The essential idea is that instead of having x and y distances, points will now be represented by the ordered pair r theta, where r is the directed distance from the origin. The origin is also sometimes called the pole. R is called the radial coordinate. You'll notice that the word radial kind of sounds like radius, and it is very similar. The idea is that r is essentially the distance from the origin. It's not quite correct because technically r can still be negative, but we'll jump into that in just a little bit. Theta is the angle measured counterclockwise from the positive x-axis. Theta is called the angular coordinate, and perhaps this name is a bit more obvious. So over here on our picture on the right, you can see that theta is clearly the angle measurement from the positive x-axis, and r is the distance from the origin. All right, and we would consider this point here to be the ordered pair r theta. In the picture, you'll notice that it does say p of r theta. Basically, all we're saying is that this point is called p. We are calling that point p, and it is represented by the ordered pair r theta. One note, if theta is negative, then we are going to measure clockwise from the positive x-axis. So if theta was negative pi over 2, for example, we would measure this distance. Okay, so let's do some examples real quick. We're going to try and plot the coordinates 1, 5 pi over 4, negative 1, 7 pi over 4, and 2, 3 pi over 2. So let's just go ahead and put some labels on this graph. So right here, we will call this distance 1 from the origin, and then this distance we will call 2 from the origin. Okay, so if we want to plot the point 1, 5 pi over 4, the basic idea is that we are going to, first of all, we are going to move on the positive x-axis over to 1, right? And then we are going to revolve around the positive x-axis 5 pi over 4 units, all right? And so let's think about what 5 pi over 4 is. So here's pi over 4. This is pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4. So the point that we need to plot is right here. It is a distance of 1 away from the origin, and it is revolved around the x-axis, it is revolved from the positive x-axis 5 pi over 4 units. All right, and so that's where P is. Q, this has a negative radial coordinate, and so basically what we do with that is we are going to move negative 1 on the x-axis. So we go over here, we consider this point, and we are going to revolve that in a counterclockwise motion, 7 pi over 4 units. So we start over here at negative 1, and then we revolve 7 pi over 4 units. And that will occur right here. Alright, and so we plot our point right here, and that is Q. Alright, so that's what happens if you have a negative radial coordinate. Alright, and for R, this has a radial coordinate of 2 and a negative angular coordinate. So what we do is we move 2 on the positive x-axis, and then we are going to we're going to move 3 pi over 2 units clockwise from that position. Alright, so we start right here, and we're going to move 3 pi over 2 units angular distance from the positive x-axis, and that is all the way up here. And so we may plot R. Let me use a different color. That's kind of hard to see, perhaps. And so R is right there. All right, so hopefully that makes sense. If not, let me know. So here are some comments. If theta is negative, then just like we did, we're going to look for the angle measured clockwise from the positive x-axis. Or perhaps if we started off with a negative radial coordinate, then we will just measure clockwise, we would measure clockwise from that position. That's what happens if we have a negative radial coordinate and a negative angular coordinate. If R is negative, then we first consider the angle measured out by theta and then go in the opposite direction. So this is one way of explaining it that also works. So let's consider this point Q again. What we could have done is notice that since the radial coordinate is -1, what we instead do is we consider the angle measurement of 7 pi over 4. So from the positive x-axis, so 7 pi over 4 units is right here. And then, if we're a distance 1 away from the origin, that means that we are in this ring. So normally, if this was 7 pi over 4, we would be at this point right here. Since this is -1 7 pi over 4, we actually would go to the opposite side of this circle. And so this is another way of explaining a negative radial coordinate. So in the prior example, we drew points on a polar grid. Notice there were concentric circles. But most of the time, we will plot points on a regular Cartesian grid. And in Cartesian coordinates, every point is uniquely represented by an xy pair. If I tell you 3, 5 as the xy pair, you know exactly where that point is. It is 3 units to the right and 5 units up from the origin. But in polar coordinates, there are actually infinitely many ways to represent a point. So you can represent any point infinitely many ways. So here are some examples. We're going to find 3 ways to express this polar coordinate. 2 pi over 4. All right, so first of all, let's plot the point 2 pi over 4. All right, so 2 pi over 4. Well, let's say that this is a distance 1, and then that this is a distance 2. Then if we go pi over 4 units from the positive x-axis, then perhaps we are right here. And then this angle measurement would be pi over 4. All right, so we could express this point as the given 2 pi over 4. Another way that we can express this point is by considering that this is equivalent to 2 and 2 pi plus pi over 4. If we were to consider an extra revolution around the x-axis, or around the circle, we would just get back to our original point if we just add 2 pi on. And that's what's done over here. You'll notice that r and then theta plus 2 pi represents the same point as r and theta, and hopefully that makes sense. So those are two different ways. We could also represent it with a negative radial coordinate. We would still need 2, but this time we would say negative 2. And if that's the case, then basically we would move negative 2 units over here, and we would need to consider what the angle measurement is to get there from here. And the angle measurement that is required to do that would be, let's count up, pi over 2, pi plus pi over 4 is 5 pi over 4, and so we could say negative 2, 5 pi over 4. So that's an option. We could have both a negative radial coordinate and a negative angular coordinate. Basically, we would start over here, and then we would consider the clockwise angle that's required to get us there. And this angle measurement appears to be, let's count this up, this would be pi over 2 plus pi over 4, which is 3 pi over 4. But it's going to be negative 3 pi over 4, since we are considering the clockwise motion from that point. So these are just a few different ways to express this point. There are infinitely many more ways. Basically, the idea would be that you could just add 2 pi to this, or perhaps 4 pi, or 6 pi, or 8 pi, or just, however many pi's you want to add on. And you could do it infinitely many ways. Alright, so it might also be important for us to be able to convert from polar coordinates to Cartesian coordinates or vice versa. So we're going to explore how to convert between the two types of coordinates. So suppose that we have the point r theta that's represented here. We could also represent this point with xy if we know what the x and y coordinates are. Alright, so based off of this picture, hopefully you have some intuition already on how to relate x, y, r, and theta. So let's suppose that we know from the beginning x and y. So if we know x and y, then we will have two equations that we can use to solve for r and theta. So the first one is the Pythagorean theorem. Notice that this is a right triangle with legs x, y, and hypotenuse r, and so we may write x squared plus y squared equals r squared. And so this basically gives us r if we wanted to solve for it. If we know x and y, we could just solve this for r. We could also solve for theta. So think about what the equation that relates theta, y, and x. The idea here is that the tangent of theta is equal to y over x. And so now, if you had y and x, you could solve this for theta. You will have to be particularly careful with this equation because it is possible that we are not in the first quadrant. And if that is the case, then you might have to be a little bit careful about what theta actually is. We'll explore this in a little bit more detail later. Alright, so if we know x and y, then we can use those two equations to solve for r and theta. If we start off with knowledge of r and theta, then there are two more equations that we can use to solve for x and y. So notice, for example, that we can relate r, theta, and y together. The equation that relates all of those is a sine function. In particular, the sine of theta is equal to y over r. If we want to solve this for y, we write that y is equal to r sine theta. And similarly for x, we may write that cosine of theta is equal to x over r, and that occurs if and only if x equals r cosine theta. So now we have the four equations that relate x, y, r, and theta. And so these are going to be the only pieces of information you need to convert between the two sets of coordinates. Okay. So here is the procedure as laid out by the book. They basically just give you these same equations. All right, so here's the note that I tried to hint at on the last slide. When you're given a Cartesian point, so you're given x and y, and you're trying to find theta, it is imperative that you determine which quadrant the point is in first. It is not true that theta is always equal to the arctangent of y over x. This is not always true, and I will show an example soon of why that is the case. Alright, so here we go. We're going to try and express the polar point to 3 pi over 4 with Cartesian coordinates. Alright, and so we write out the equation that will give us x. This is x equals r cosine theta. R in this case is 2. Theta is 3 pi over 4. Alright, so cosine of 3 pi over 4, that is going to be negative root 2 over 2. And this, of course, is just negative root 2. So that's our x-coordinate. Our y-coordinate is r sine theta. R is 2. Theta is 3 pi over 4. Sine of 3 pi over 4 is positive root 2 over 2. And so our x, y coordinate, therefore, must be negative root 2, root 2. For the next example, we are starting with the Cartesian point and converting to polar coordinates. Alright, so we start off with r squared equals x squared plus y squared. So if we take the square root of both sides, so let's just go ahead and plug in what x and y are. Actually, I want to do this slightly differently. We know then that r squared is equal to 1 squared plus negative 1 squared, because that's what x and y are. And that means that r squared is equal to 2. Then we take the square root of both sides. The square root of r squared is the absolute value of r. But since we know that r is non-negative, we may write r equals root 2, because the absolute value of r is equal to just r. Alright, so we have our radial coordinate. The next question we should ask ourselves is, what quadrant is Q in? Alright, so the quadrant that Q is in plays a pivotal role for us. Let me actually go orange. The answer to this is that it is in quadrant 4. Let's use Roman numerals. And so quadrant 4, of course, is this guy. And the basic idea now is that with this information, we can use that to figure out what theta is. We are also told that theta is between 0 and 2 pi, so this will give us the ability to come up with a unique choice for theta, rather than saying that theta could be chosen amongst an infinite set of choices. Alright, so we're going to use the equation that tangent theta equals x over y. X over y in this case is 1 over negative 1. Sorry, this should be y over x. So this is negative 1 over positive 1, which is negative 1. And so the question we must ask ourselves is what... Let me actually change the questions to a different color. Let me make these green. What angle in quadrant 4 satisfies tangent theta equals negative 1? And the answer to this is theta equals 7 pi over 4. And the idea for that is that we have to go pi over 2, pi, 3 pi over 2, and another pi over 4, which gives us 7 pi over 4 in total. Note that, let me do this in red, this theta, 7 pi over 4, is not equal to the arctangent, the inverse tangent, of negative 1. This thing, the inverse tangent of negative 1, if you were to plug that into a calculator, you would actually come up with negative pi over 4. And that is not in our domain. Alright, and so this causes us a little bit of issue. Moreover, if we were to have attempted to consider a point that was over here, it wouldn't be in our domain at all, and so we would really have to be hesitant about using this inverse tangent. And so it is very important that whenever you use this equation, the bottom line is you have to ask yourself this question. What angle in this quadrant, or whatever quadrant your point is in, satisfies your equation? All right? And so it is very important that you figure that out. Don't just plug it into a calculator. All right, let's continue. So now we're going to consider drawing curves and polar coordinates. So we know what polar coordinates look like, so we're going to try and figure out what curves might appear as. So let's once again reconsider Cartesian equations. The curve y equals 2 is one of the simplest curves that we can come up with. Specifically, it is a horizontal line two units above the origin. The reason I bring this up is because it is y equals 2, which is a constant function. So normally we say like y equals f of x, right? In this case, there is no x, and so the line that is drawn is just horizontal. If we use similar thinking, the polar equation r equals 3 means that we have a constant radius of 3. So in other words, what we are essentially drawing is a circle of radius 3. There is no angle to influence it. It occurs at all theta, a circle of radius 3, centered at the origin. Let's draw that. Let's just go ahead and use this. Whoops, I don't want that color. Let's go red. Beautiful. Where this is 3. So in other words, the distance from here to the from the origin to the edge is 3. Okay. And the equation theta equals pi over 3. So this basically means that your theta measurement is always the same. There is no r that restricts it. And so the constant value for theta equals pi over 3 will actually be just a line going through the origin of that is pi over 3 units from the, or pi over 3 radians from the positive x-axis. And that would be the equation. A line through the origin with an angle from the positive x-axis of pi over 3. And so let's draw that quickly. Alright, so that's the idea. So these are two of the simplest types of polar functions that one can draw. A constant function of r and a constant function of theta. We can draw circles and we can draw lines very simply using this sort of thought process. Let's complicate it a little bit. So now let's consider the curve r equals theta, where we consider only non-negative theta values. This actually is going to create a spiral, and as theta increases, r increases as well. So at theta equals a very small number, so let's say at pi over 4, we're going to be right here, and then r will be pi over 4 away. This coordinate right here is the angle measurement theta equals pi over 2, and r equals pi over 2 as well. And same thing here, it would be theta equals pi, r equals pi, and as you can notice, as theta grows, r grows as well, which is why this creates a spiral. Neat curve. I'm not sure how much practical application it will have in your studies, but it's a nice thing to look at. So if we wanted to write this in Cartesian form, we would actually need to use the conversion equations that we learned earlier. So let's consider that. We're going to convert the polar equation r equals 10 cosine theta plus 24 sine theta to Cartesian coordinates and describe the corresponding graph. Alright, so the basic idea, let's remind ourselves what equations we have to work with. We have that x squared plus y squared equals r squared. We have tangent theta equals y over x. We have x equals r cosine theta, and y equals r sine theta. These are the four fundamental equations that we can use to transform our polar function into a Cartesian function. Alright, so there's a variety of techniques that one might consider trying. Right now, there's nothing in this equation that's super nice to work with, so we have to algebraically manipulate it somehow. One thought that you might have is to isolate cosine of theta here, and then you would get cosine of theta equals x over r, and so you could write cosine of theta equals x over r, and then sine of theta equals y over r, and then perhaps you could multiply both sides by r, and you would get r squared equals 10x plus 24y. And then r squared has a, whoops, I forgot a square earlier. Whoops, r squared. R squared has a simple relation to x squared and y squared, so we could do that. And so that's one way to go about it. An equivalent way, and one that I actually see easiest, is to actually just multiply both sides of this equation by r. So we can write that r squared is equal to 10r cosine theta plus 24r sine theta. Then the idea is that r cosine theta is x, and r sine theta is y, and r squared is x squared plus y squared. And suddenly, if you replace all of that you no longer have any r's and thetas. They're all gone. And so we have successfully written this in terms of Cartesian coordinates. But it's still wanting us to describe this graph that we have just created. So let's consider manipulating this a little bit more algebraically. All right, so one thing we can do is we can subtract the 10x and the 24y to the left-hand side. So we would get x squared minus 10x and y squared minus 24y. You'll see in a second why I'm leaving these gaps, equals 0. I think I actually want to leave a slightly larger gap. All right, so one thing we can do with x squared minus 10x is we can complete the square. So remember that in order to complete the square, we consider this number, the coefficient of the x term, we take half of it and we square that number. So half of this is negative 5. Negative 5 squared is 25, and we are going to add and subtract the number 25. So we don't change the fundamental value of our problem. And then we can do the same thing with this guy. We consider half of negative 24. That is negative 12. We square that, we get 144. So we're going to add 144 and subtract 144. All right, now notice that this thing here is a perfect square, as is this thing. We may write that x squared minus 10x plus 25 is just x minus 5 quantity squared minus 25. And then y squared minus 24y plus 144 is just y minus 12 quantity squared minus 144 equals 0. Let's add 25 and 144 to the right-hand side. We're going to get x minus 5 quantity squared plus y minus 12 quantity squared equals 169. And if you know your times tables, 169 is a perfect square. Specifically, it is 13 squared. So this is a circle. This is a circle centered at 5, 12 with a radius of 13. So in general, remember that the equation for a circle is x minus h squared plus y minus k squared equals r squared. So therefore, this is a circle centered at 5, 12 with radius 13. All right, so from this bizarre looking radial graph, we were able to write this in a form where we got a standard circle equation. Right? And so anytime you're given a polar equation and you're asked to convert it to Cartesian equations, the basic fundamental idea is to algebraically manipulate this somehow so that way you can utilize these four equations. Perhaps you multiply both sides by r, perhaps you group certain terms, perhaps you square both sides. Whatever you need to do to get it in a form where you can use this information. All right, so that's one example on how we convert from polar to Cartesian. Here's a quick summary whenever it comes to circles in particular. The equation r equals a, where a is a number, describes a circle of radius absolute value of a centered at the origin. And the equation r equals 2a cosine theta plus 2b sine theta, that is what we have here, where this is 2 times 5 and 2 times 12. Describes a circle of radius square root of a squared plus b squared. So in this case, it's square root of 5 squared plus 12 squared, centered at the coordinate AB, which was 5, 12. So yeah, that's how one can draw circles in polar coordinates. So this only describes circles that are centered at the origin, or circles that pass through the origin, like this one. There are equations that describe circles that don't satisfy either of those criteria. For example, this circle, which is neither centered at the origin nor does it pass through the origin. But those are more complicated. Okay, so now let's consider the task of plotting a polar curve. All right, so if we are given a variety of theta values, so first of all, we're asked to graph this function, r equals 1 plus sine theta. So essentially the idea is that theta is our dependent variable and r is our independent variable. The other way around. Theta is the independent variable, r is the dependent variable. Yeah. If we come up with several choices for theta, we can use a table to figure out what r needs to be for each of them, and then plot those in the appropriate graph. So let's give that a shot. If theta is equal to 0, then 1 plus sine of 0 is just 1. If theta is equal to pi over 6, then 1 plus sine of theta is equal to 1 plus sine of 1 plus 1 half, which is 3 over 2. If we have pi over 2, sine of pi over 2 is 1, and so we would get, we would get 2. 5 pi over 6, we would once again come up with 3 halves. Sine of pi is 0, so we would get 1 plus 0, which is 1. 7 pi over 6 is negative 1/2, so this would actually be 1/2. And then this would be 0. I need to make sure I space these correctly. Right. Might even be prudent to draw some horizontal lines in here. Yeah, it looks a little bit nicer. For 11 pi over 6, we once again come up with 1/2, and for 2 pi, we will get 1. All right, so let's attempt to graph this. At theta equals 0, we are... So let's first of all start with the r coordinate. That's the easiest thing to think about. So we start at r equals 1, that's right here, and we are going to move theta equals 0 units, 0 radians around the circle, so we just stay in place. So the first point that we're going to plot is just this one. All right, at r equals 1.5, 3/2, that's right here, and then we revolve pi over 6 units from the positive x-axis, that's this point. So we plot the point right there. At r equals 2, we are going to rotate pi over 2 units from the positive x-axis, so we get this point. We're going to keep doing this process. Oops, that's the wrong one. It should be right here. And then right here. Alright. And then let's think about what happens at 7 pi over 6. So at 7 pi over 6, we have radius 1/2, so that's this point. At 3 pi over 2, so we look at 3 pi over 2, we are 0 units away. We are r equals 0, so we started at the origin and then we revolved around and still stayed at the origin. So that is this point. And then we would plot 1 right here, and we would eventually end up back at the start. If we connect all of these points together, we end up with a curve that looks a little something like this. It's awful. Let me try again. I want to make sure it looks somewhat nice. That's not too bad. And so this shape is called a cardioid. And I kind of like the word cardioid. It's got 3 consecutive vowels in a fun manner that you don't normally see. And it also kind of looks like a butt. And so that's kind of fun. Or maybe a heart, you know, whatever you want to see. But yeah, this is a cardioid. In general, a cardioid will be r equals 1 plus either sine of theta or cosine of theta. Perhaps they have a minus here. Perhaps this number changes. Perhaps there's a coefficient in front. But this general shape is a cardioid. All right, and so this is how one might go about plotting a polar equation like this. An alternative method, if you have a function of the form r equals a function of theta, so this will not work if you have something like r equals 2 to the r plus theta, because this is not in the form of r equals some function of theta. All right. So if this is the case, if you have something that looks like this, then what you could do, an alternative procedure, is to graph r of theta as if r and theta were Cartesian coordinates, with theta on the horizontal axis and r on the vertical axis. So you treat theta as x and r as y. And then you're going to choose an interval for theta on which the entire polar curve is produced. And so what that might look like is if you are trying to plot r equals 1 plus sine theta, it would just be the sine function shifted up 1 unit. So this is your normal sine function. Here is the sine function shifted up 1 unit. All right, so that's what happens if we were to plot it as if they were Cartesian coordinates. The second step is to use the Cartesian graph in step 1 as a guide to sketch the points r theta on the final polar curve. So essentially, what we mean by that is that we would think about what happens at pi over 2 and then look at the associated r value and plot a point. All right, so first of all, at theta equals 0, the radius is 1. So at theta equals 0, that's along the x-axis, the radius is 1. And so we would just plot a point right here. And then we notice that the radius increases slightly as theta gets larger, right? It increases until you get to pi over 2. Then it starts to decrease a little bit. So the radius will continuously grow and get a little bit farther away as you go around this curve. All right, and you can actually see the corresponding colors here. So this pink section corresponds with this pink section. And this blue section corresponds with this blue section. All right, so then once you get to pi over 2, we notice that the radius starts to decline a little bit. So you'll notice that's what happens here as well. The radius starts to decline. This green line is associated with this green line. And then eventually you get down to a radius 0. So that's actually this point. And then for this final leg of the journey, we notice that the radius starts to increase a little bit from 3 pi over 2 to 2 pi. And so at the angle measurement of 3 pi over 2, you're right here. At 2 pi, you're on the x-axis, and so in between, you've got this little piece. All right, so this is an alternative graphing method. It's called the Cartesian to polar coordinate graphing method. So let's do an example. Suppose that we are... what am I trying to say? I don't know why I say that Cartesian and polar graphs for this are given. I only give you this one. Okay. Yeah, so I don't give you the Cartesian one. Okay. Anyway, I give you this function, and then I plot it. Oh, graphs. Yeah, sorry. It's been a while since I've looked at this. Yeah, I give you this Cartesian graph over here on the left. This is the way that you would graph this function in Cartesian coordinates. If theta was the x variable and r was the y variable, it would look like this. And if you were to plot this in a polar graph, it would look like this beautiful little flower over here. So what we're going to do is we're going to mark the associated points on this left graph with this right graph. And it's not entirely obvious. It's a little bit tricky. So we start, let me switch to a nice green. We start with this point A down here. All right, so you'll notice that the radius is about negative, let's say negative 0.75. So what we would do is we would consider going on the x-axis negative 0.75 units. And then we would rotate counterclockwise 0 radians. and so we just stay in place. So this point here is A. All right, for B, for this point B, we are at a radius of 0. So we are right here. And then we revolve, let's say, pi over 8 units around the pi over 8 radians from the positive x-axis. But since we're at the origin, we're not really doing anything. It's just going to stay at the origin. So this point right here is B. So that point is B. All right, let's consider the point C now. This has a massive radius of about let's say 1.25. All right, so we're going to come over here to 1.25, something like that. And then we revolve around, or we revolve from the positive x-axis, pi over 4 units. And so that's going to be right here. And so this point is C. All right. And then the point D, once again, this has a radius of 0. And so we are again going to be back here at the origin. So that point is also D. All right, we get to E. E has a radius of about negative 0.75. So we consider negative 0.75. Maybe that's around here. And this is pi over 2 units clockwise. So pi over 2 units counterclockwise is this one. So we are right here now. So this is the point E. For F, so notice if I were to again consider points here, these would just go back to the origin. And so I would have a lot of points pointing toward the origin. So we're going to consider F, which is once again at a radius of about 1.25, so maybe over here. And then this is 3 pi over 2 units in the counterclockwise direction. So that's this guy. So that is F. And if we continue to fill out this, this picture, what the points are going to look like is that, so here's how the curve is ultimately sketched out. We start with a negative radius A, and then it revolves around. So normally the angle measurement would be really small, so maybe like an angle measurement like that. You guys see this? This is a small angle measurement. But since r is negative, we would end up on the opposite end, so that's why the angle, or the curve, is sketched out starting here, going this way. We go through the origin, and then we come up here to point C. We come back, and then we would actually go down the flower petal. We would come down here to point E. We would go back up, back through the origin, up here to point F, and then over here, and then down, and then back up, and then over to the bottom right, and finally we land back at A. And so that's the way in which this curve is sketched as an increasing function of theta. And so let's just go ahead and plot the remaining points on this graph. This would be G, H would be over here, I would be up at the top, J would be this bottom right one, and K would actually land back at the start. All right, so hopefully that makes sense. If not, be sure to let me know. So let's do another one. This one is a little bit weird. This curve is called a lemniscate, and it'll look somewhat familiar after we've fully drawn it out. So what we have to start is r equals plus or minus 3 root cosine theta. And we're going to, so we have this over here in the Cartesian graph, and we're going to plot it in a polar grid. Okay, so I am going to get the associated colors for this. So the first thing we should consider is that at theta equals 0, we have a radius of 3. So radius of 3, that's this point, and a angle measurement of 0, so that is the correct point. Then let's consider what happens as the angle increases slightly. As the angle increases slightly, the radius will decrease a little bit. So it starts to decrease a little bit. So it does something like that. Until we get to a radius of 0 at pi over 2 units. So whenever theta is at pi over 2, so we get a bunch of angle measurements, and then whenever theta is at pi over 2, we are back at the origin. Okay, so this is going to look like this. So notice at this angle measurement, the radius is largest. At this angle measurement, the radius is smaller. At this angle measurement, the radius is even smaller. At this angle measurement, it's even smaller, and then finally at pi over 2, it is just 0. Okay. So let me actually write down this line as well to just show you the correspondence. So this blue line here corresponds with this. This blue line here corresponds with this blue line here. Okay. Let's consider the pink portion. So the pink portion starts with a radius of -3. And so we're going to move -3 units over here on the x-axis, and it will have an angle measurement of 0. Notice that the angle measurement is theta equals 0, and so we don't move. Then the radius decreases in magnitude as the theta values increase slightly. So as theta increases a little bit, so we're going to consider clockwise movements, the radius will decrease in magnitude slightly. And so what this pink portion will do is it will look like this. And this pink line corresponds to this pink line. Okay? These aren't actually parts of the graph. Perhaps it would be best to erase them. But I think I want to leave them to just show you that like this angle measurement corresponds to this angle measurement. Okay, anyway, let's do the other two portions. So for green, notice that at 2 pi, at the angle measurement of 2 pi, which is this angle measurement, we have a radius of 3, which is this point. So we have a point right here. Alright, so as the angle measurements decrease slightly, as they decrease from 2 pi, the radius gets smaller and smaller. So as the angle measurements are slightly less than 2 pi, the radius will get smaller and smaller, and so this will look like that. And finally, the orange piece, if you haven't guessed it already, will do the exact same thing as all of these others. It will look like this. And this is a lemniscate. You'll notice that it looks like an infinity sign. Alright, so yeah, this is how one would draw this polar graph. And this is something that is very difficult to express with Cartesian coordinates. And so the polar graphs are advantageous. All right, and the final slide for this chapter is just a quick note about symmetry. We want to make the note that in polar coordinates, there are several different types of symmetry. There is symmetry about the x-axis whenever r theta and r negative theta are both on the graph. So if both of these points are on the graph for every choice of theta, then there is symmetry about the x-axis. This is true, for example, with a circle, because if r is equal to 5, for example, then certainly r and theta equals pi over 2 and r negative pi over 2 will be on that graph. Okay. Symmetry about the y-axis occurs if r theta is on the graph whenever negative r negative theta is on the graph. So if that is the case, then you can see in this diagram down here that there is symmetry about the y-axis. And there is symmetry about the origin if r theta and negative r theta are both on the graph. If this is true, then there is symmetry about the origin. All right. This is all I have for you for section 12.2. If you have any questions or comments, be sure to leave those down below, and I'll be sure to answer those as quickly as I can. Otherwise, just feel free to send me an email. And until the next section, I will see you later. All right, have a great day, everyone.